There, now we're recording. All right, so here's my quotient rule. I'm going to go bottom times the derivative of the top minus top times the derivative of the bottom square. Bottom is 5 cosine of 5y. Top is just a function of x, so its derivative is just going to be 2. Then the other way, the top is a 2x. And now here's where the implicit differentiation comes in. I've got a function of y down there. So start with the outside. The derivative of the cosine is minus the sine. So we have minus 5 sine of 5y. Now I'm inside the parentheses. And we get 5 times y prime. All over the bottom squared. Let me go ahead and square it and get 25 cosine squared of 5y. So let's see, I'm going to put the outside terms together. We're going to put the 5 times the 2, make that a 10 cosine 5y. Here I'm going to take this minus sign and that one and make it plus. And then I'm going to have 2x times 5 times 5. So I've got plus 50x sine of 5y times y prime all over the 25 cosine squared of 5y. And in here goes our y prime from the first step. Okay, we're replacing that in terms of that stuff over there in the 2x divided by 5 cosine of 5y. Okay. I'm going to simplify. You're going to tell me where the stuff comes from. Firstly, I've got 10, 50, and 25. They're all divisible by 5. So I'm going to knock a 5 out of everything.
Also get rid of the bottom.
We need bottom completely.
Cosine 5y. Is that the thing, or is that not a thing?
No, because the plus sign.
Yeah, but you can turn that into a tangent.
I'm going to turn this one into a tangent. All right, so I'm going to have 2 cosine 5y. Then I'm going to take this 10x times 2x and get 20x squared. So plus 20x squared. And then when I multiply these together, this will be on top. I'll have a sine of 5y over a cosine of 5y. It's going to give me a tangent of 5y. Somehow I lost that 5. I'm going to take care of that next. So that's a tangent of 5y. This 5, I'm going to divide into the 10 and get me a 5. So this 20 becomes a 10. And then I've got that over 5 times the cosine squared of 5y. Okay, just made it a little bit prettier. It's not worth really doing. I had a little bit of room left on the board. I thought I'd use it.
Can you explain again what you did to get this 10x squared 10?
Let's see, I've got, first I had the 50 here and I divided everything by 5.
Right.
And so that gave me a 10. Then I remembered I had a 5 down here. So that 5 goes into the 10. Maybe I've got the wrong number. 5 goes into the 10 2 times. So this should be a 2 times 2. This should be a 4. 4. Right, that's a 2 right there. Thank you very much.
5 and 2 are very distinct.
And because it's sine over cosine, that's why you just combine it to 10.
Yeah, that got rid of the fraction on top, so it made it look like it's all
Okay.
nice on one line.
I like that.
Okay? Okay, so let's take a break and answer the Wegler questions.
Triple derivatives.
Triple derivative of?
There's 2 of them.
Oh, that was so much fun.
I tried twice and said no.
Bryson said no. That's really not persevering, is it?
No, I'm very lazy.
The numbers got really big.
On one of them? So I'm kind of frightened. You're gonna, wipe me out here. And I told you I needed more coffee. All right. Fire when ready.
Double check it real quick, so I don't get the problem wrong.
Actually, I think I have it. It's in parentheses 11 minus 5 t squared.
I'm sorry, t
T
squared?
squared. And then to the 1/2.
We want 3 derivatives of this?
Yes.
Okay. Maybe that's where simplifying might be useful. Find the third derivative. Do you know what number this is?
Oh, second to last one, 17.
17? Okay, so we've got the general power rule first. Bring the 1/2 down, raise it to 1 power less. Y prime looks like 1/2. 11 minus 5t squared to the negative 1/2. And then we go inside and take the derivative and get a negative 10t. Is that correct?
Yes.
So it helps to simplify. Let's send the 1/2 through the negative 10 and get a negative 5t. Did you leave this here and do a product rule, or did you do a quotient rule?
I did a product rule.
That's probably where the mess comes in.
Yes.
The quotient rule might be pretty easy to simplify.
Really?
Maybe. Maybe. Have I asked you the product rule? You left me the product rule? You want to try quotient rule then?
I did not.
Might be more fun.
Yeah,
Let's
let's
try
do it.
Let's do it.
What do you see there, Lacey?
Because a negative exponent, and I know when I square that, I'm gonna get a positive 1
Oh, yeah.
in my denominator squared. Maybe it makes it nicer. Not, then what have we got to lose? You said the other one was messy. So I'm gonna do it like that and do the quotient rule to get y double prime. So we take the bottom, 11 minus 5t squared to the 1/2. Here the top is just a negative 5. Minus the top, well, the top is negative, so that end result will be a plus 5t. And now we'll do the chain rule again, same derivative, 1/2, 11 minus 5t squared to the negative 1/2 times negative 10t. All over 11 minus 5t squared, 1/2 squared will yield me to the first power down there. Did I lose anybody? Okay, I'm going to simplify. I'm going to take this negative 5 and put it out front. I'm going to take half of that 10 and give me a negative 5. So that's a negative 5t times a positive 5t. That's going to make that a negative 25t squared. So what I said, it was a negative 25t squared. We'll put this downstairs because I'm going to do a lot of simplifying. Before I take another derivative, I want to clear the fractions out of the numerator by doing
Multiply them,
I'm going to multiply everything by this. We're going to multiply all these terms by the 11 minus 5t squared to the 1/2.
That's so nice.
Top and bottom. Yeah, when you multiply line basis, you add the exponents. So when I distribute that through here, this becomes 11 minus 5t to the first power times that -5. Cancels that denominator, so I just have a minus 25t squared. And what's the power going to be on the bottom? I understand yawn. That's 3/2. Add exponents again. Yes, sir.
So on the top, when you multiply the first term and it just became like 11 minus 5t squared, how come the -5 didn't change out in front of it?
Then why should it? What would it change to? I mean,
This is in Arkansas. Last I checked.
I don't know. I don't know why it would change. When you multiply three things together, you can take any two of them and multiply them and then multiply by the third thing. That's the associative property of multiplication. A times B times C is the same as A times B times C. Multiply A times B times C, or you multiply B times C times A.
Okay.
So I'm holding the 5 and multiplying the last two together. Okay, so that simplifies still a bit more. This is going to be, look, positive 25t squared. There's a negative 25t squared.
Well, how do you're kind of good at this.
So all that's left on top is a negative 55. And how do you think I got good at this?
Cheating.
I did a lot of it. But look, now the other derivative is easy. Right? I've got a constant on top, so I don't even need to do the product or the quotient rule. I can do the derivative by moving that to the top and just doing the power rule. Move that to the top, and then we'll do the power rule on it. You need to write bigger. Is that east?
You still have to change it, though, right?
Yeah, we'll still do the chain rule. That's a negative 3/2 power. We'll write that bigger. Practice, unfortunately placed. Would it have been too hard to put these closer together? Closer together. All right, so from here to get the third derivative, we just use the general power rule. Y triple prime.
That's crazy. Triple prime is the easiest of like all.
Yep. Oh, now I've lost it. I don't know where to put it. Let's go back to the whole board. Okay, so we're going to bring the negative 3/2 down, multiply it with the negative 55. So I'm going to get a positive. Let's see, 15, negative 165 over 2. Or positive 165 since I've got a negative times a negative. Then I raise that to 1 power less, 11 minus 5t squared to the negative 5/2. And the derivative inside is a negative 10t. What you want me to multiply by? 165 times the 5. Negative up front. 2 is going to go in there 5 times. We'll put that back on the bottom. So we're going to get a negative, whatever 5 times 165 is. 825-ish. The 2 canceled. It's negative from here. This has a minus power, so we put it back on the bottom. So that was the point of putting this problem on there, was that the simplifying can help you do the calculus part. Simplify it up a bit and make it a little bit easier on yourself.
I have one simple question. At the bottom of y double prime, where did the negative 55 and then later come from?
That times that gives me the negative 55. That times that gives me positive 25t squared. And I got a minus 25t squared. So is the other one also a y triple prime?
Yes, and this time there was no like thing in the middle. Last time you entered, the first one you entered like your progress to make sure you didn't mess it up in the first step.
Ah,
This one it just went straight to triple prime.
okay.
I can check what it is. Actually, oh, I have it written down. Okay,
Ready?
it's a fraction this time.
Okay.
It's 2 minus 5x over 2 plus 5x. This is 18 Austin.
We want 3 derivatives of this. That x is looking bad. Get back up there. All right, quotient rule. Bottom, 2 plus 5x times the derivative of the top. Negative 5. Minus the top, 2 minus 5x times the derivative of the bottom is a positive 5. All over the bottom squared. Now we're going to multiply this out. Negative 5 times 2 gives me a negative 10. Negative 5 times the 5x gives me negative 25x. Let's keep this sign, multiply by the 5. 5 times 2, that becomes a negative 10. 5 times this is a negative 25x, but with that becomes a positive 25x. That is convenient. 25x's add each other out, and we just have a negative 20 over that. And again, when your numerator is just a constant, you can just move that denominator up, change the sign on it, and we'll do the power rule from here on out. Take that 2 plus 5x to the negative 2. So I've just got a constant times a function. So the next 2 derivatives are going to be kind of quick.
But you knew that they would cancel out. if
I
you did
did.
that. Yeah.
Yeah, that typically happens when you have the same degree on top as on the bottom. All right, so you ready? I'm just going to do the power rule. Y double prime. I'm going to take negative 2 times 20. They're both negative, so I get a 40. Then 2 plus 5x to the negative 3. The derivative inside gives me a 5. So put the 5 with the 40 and get 200. And I'll do the next derivative the same way. I'm not going to write this as a fraction. I'm going to just use a constant times a function rule. So finally, y triple prime. Negative 3 times 200 is negative 600. 2 plus 5x to the negative 4 times another 5. And now I'll write it with positive exponents. 5 times 6 is 30, so this is going to be 3,000, and it's negative. And then we have 2 plus 5x to the 4th on the bottom. I should have did that one before this one. Okay,
It's helpful now knowing that you don't actually just hate us, you want to slowly simplify.
yeah, I mean, there's the point of every now and then simplifying is maybe get you to try it every now and then, just see if it makes your life easier. Anybody else? Anybody else got any whiteboard questions? Okay, so we are going to use implicit differentiation to derive the formulas for inverse trig functions. Let's pick it back up. This is still section 3.6. I'll try to open you a web work on 3.6 today.
Is the one open right now due Wednesday?
I don't
Not due till next
remember. Is
week.
that right?
Yes, I think it's still October 6th.
I had almost randomly picked these dates, so I don't remember them.
Roll the dice.
Okay.
East. Okay. Section 3.6. Still doing implicit differentiation, but we're going to use implicit differentiation to take the derivatives of inverse trig functions. And in doing this, we'll generate formulas for the derivatives of inverse trig functions. We have 6 inverse trig functions, but you're only going to need 3 formulas because there's some kind of handy-dandy connection between them. So let's see, the first one. Y is equal to the arc sine of x. The arc sine of x came from trying to find the angle that we would take the sine of to get x. So I'm going to rewrite this line in its equivalent form. To say y is equal to the arc sine of x is the same thing as saying the sine of that number y gives us x. Right? So now I'm looking for y prime, but let's find y prime from here using implicit differentiation. So now we're going to go over here and we're going to take the derivative of this with respect to x. What will the derivative of the sine of y give you? So sine of y times? So on the left side, you get cosine of y times y prime. And on the right-hand side, 1. So y prime is equal to 1 over the cosine of y. But I'm going to go further. If I know the sine of y as a function of x, then I certainly know the cosine of y as a function of x. Sine squared plus cosine squared is 1. That's one way to derive this. Or the other way is just make a right triangle. Kind of picture what's going on. Here's the angle y with the property that the sine of that angle is x. If you remember, the sine is the opposite over the hypotenuse. So I can put an x here and a 1 there. And if I want to use that triangle to tell me what the cosine of y is, then I need to get the adjacent side as a function of x. What would it be?
Y. Wait. So right, yeah. Oh.
Square root of 1 minus x squared. And so there it is. The cosine of that y is the adjacent over the hypotenuse. The adjacent over the hypotenuse, and the hypotenuse is just 1. So what we've discovered here is that if y is the arc sine of x, its derivative is 1 over 1 minus x squared. So we just decided that the derivative with respect to x of the arc sine of x is 1 over the square root of 1 minus x squared. And what if we had something in there more than just x to the first power? We put a u there, or u is a function of x. Use a function of x, then by the chain rule, the derivative of the arc sine of u is 1 over the square root of 1 minus u squared times u prime. So you might want to keep that as a formula. Now let's do the same thing to find the derivative for the arc cosine of x. So we write the y is equal to the arc cosine of x in its equivalent form that says the cosine of y is x. Start from there, use implicit differentiation and take the derivative of both sides. What was the derivative of the cosine?
1 over root 1 minus x squared.
No,
Oh,
cosine, during cosine,
Negative sign.
negative sign. So we get negative sine of y times y prime. And on the right-hand side, we just get a 1. So y prime is 1 over the sine of y, and it's negative. Someone go ahead and put the negative in the numerator. And then again, if I know the cosine of y is x, I can figure out the sine of y as a function of x. So I'll draw the right triangle to help you remember that. There's y. Cosine of that angle y is the adjacent over the hypotenuse. In order to find the sine of this, I need the other leg. Just like before, the other leg's going to be the square root of 1 minus x squared.
In that triangle on the feature, getting the x to 1.
From here. Cosine of y is x.
So opposite over adjacent.
So the cosine of this angle y is x over 1.
I mean, adjacent over one. All right.
And then this side comes from the Pythagorean theorem. Leg squared plus leg squared is 1. Now that's going to be the sine of y because my hypotenuse is 1.
So the exact same thing. But negative.
The exact same thing but negative. So we don't need to remember this formula. The derivative of the inverse cosine of y is minus the derivative of the inverse sine.
So are we gonna have some problems, just trying to like look ahead? We're gonna have some problems where we wanna get to the arc cosine of x, maybe simplified or something, so that we can take derivative and get.
Now this is going to show up in problems. We take the derivative of inverse cosine. Right, so add it to your formula. But this one's the same as this. Derivative of the arc cosine is the same as the derivative of the arc sine, but it's gonna have a minus in front of it. The same thing's gonna happen with the arc cotangent and the arc cosecant. They're gonna have the same derivative formulas as the inverse tangent and the inverse secant, but the numerators will be negative. So just trust me on that one. So we only need 3 formulas. Derivative of the inverse sine, the derivative of the inverse tangent, the derivative of the inverse secant. Their co-functions are just minus their formulas. So let's make that statement. The derivative with respect to x of the arc cosine of u is minus 1 over the square root of 1 minus u squared times u prime. Or it's just minus the derivative of the arc sine.
You probably can use that to cancel some stuff.
We don't need to worry about minuses. Okay, so I'm going to go to the next board. Let's do the same thing with the inverse tangent. So I'm going through these steps in case you ever forget the formulas. You can start the same way and just generate the formulas yourself. All right, so third one. If y is equal to the arctangent of x, we rewrite that by saying that the tangent of y is x. And then we start from there and use implicit differentiation. All right, who remembers the derivative of the tangent?
Secant squared.
All right, so we get secant squared of y times y prime over here. And we get a 1 over there. So y prime is going to be 1 over secant squared of y. Which is, we're going to figure it out from here. Tangent of y is x. So in my right triangle, I've got the adjacent side, the opposite and the adjacent side have to simplify to x. So how about we put the x here and the 1 there? And what's the hypotenuse going to be?
1 minus.
Not
Secant-
minus.
secant is
Leg
1
squared
over
plus
cosine.
leg squared is hypotenuse squared.
1 over cosine, so it'd be hypotenuse over 1.
Well, let me get the hypotenuse. 1 squared plus x squared is the hypotenuse squared. So I'll put the square root on it. Okay? Now I'm going to put the secant in here, and the secant is hypotenuse over adjacent. So the secant is just going to be that, and then I've got to square it.
Oh, that's even more.
And so here's the formula for the derivative of the inverse tangent. 1 over 1 plus x squared. Use the radical sign when I square it. So let's write it as a function of u. The derivative with respect to x of the arctangent of u is going to be 1 over 1 plus u squared. Then the chain rule will give us a u prime. And then trust me that the derivative with respect to x of the arc cotangent of u just has a minus sign right here. So I won't even waste ink on that one.
What you said, secant, or not tangent. and then-
The arc cotangent just has a minus sign here. So the co-functions, sine, cosine, tangent, cotangent, same derivatives but with a minus. So secant and cosecant. All right, so you ready for another one? Got our secant function to do, our arc secant. So we start by saying y is equal to the arc secant of x means the same thing as secant of y is x. And we'll take the derivative of both sides. So I need to remember the derivative of a secant. Secant tangent, so we get secant of y, tangent of y times y prime. And on the right-hand side, we get 1. Solve for y prime. Then we get 1 over the secant of y times the tangent of y. We're going to try to write the right-hand side strictly as a function of x. And we're halfway there. The secant of y is x. So this is going to be replaced by x. Now let's draw the picture and figure out what the tangent of y is. Let's see, secant is hypotenuse over the adjacent. So I can write the x and the 1 here. And now this squared plus this squared has to be that squared. 1 squared plus whatever squared has to be the x squared. So if I solve for this, b squared is x squared minus 1. So this side is the square root of x squared minus 1.
Secant y equals perfect.
Yep. So here's the function of x. We said secant of y up here is x. Use my picture now and tell me what the tangent of y is. Square root of x squared minus 1. So there's the formula for the derivative of the inverse secant of x. 1 over x times the square root of x squared minus 1.
Where did the x come from? I'm sorry.
The secant of y right here. Secant of y is x from the very first line at the top of the board. Okay? So we write that in terms of the general formula, the derivative with respect to x of the arcsecant of u should be 1 over u times the square root of u squared minus 1. Times u prime. Got my chain rule. A lot of times you're going to see this on the formula. And that's to keep this function defined in the same places as that one. So we'll put the absolute value bars on there. A lot of times you'll see it without and just the assumption that this is a positive quantity. This thing out here needs to be positive. Because what? Because if it's negative, then you've got the arc cosecant. Put that in absolute value bars. So you need these 3 formulas. U prime over the square root of 1 minus u squared. The inverse sign has the variable squared behind the minus. Just like if you do the Pythagorean identity, that cosine squared is 1 minus sine squared. The arctangent doesn't have a square root, has the sum of the 2 items here. And the arcsecant has both, no square root and a square root, but the variable squared is in front. So that refers to the identity that secant squared minus 1 is tangent squared. So those 3 are all you need, and you'll have success in taking derivatives. Some examples here.
When you take, so arcs, derivative of arc cosine is just the u in the denominator is negative.
Yeah, this is, there's the derivative of the arc cosine of x. The minus 1 on top instead of the negative 1. Okay? next example. We'll go back to the east board. Find f prime of x. The first one, f of x is equal to the arctangent of 4x plus the arcsecant of e to the x. So you can do this term by term. Down there at the bottom of the board, the derivative of the arctangent of u is 1 over 1 plus u squared times u prime. So the u is the 4x. That one has as its derivative u 1 plus u squared. We can go ahead and put u prime up there if you want. So in our example, I'm going to have 1 plus 4x all squared. And now derivative of 4x gives me this 4. This next one,
Wait. Oh, I'm sorry. There it was.
I'm using this.
Yeah,
I just scooted that over. I'm gonna do the same thing here. I'm gonna scoot the u prime on top. So this next one's gonna look like u on the bottom, a square root of u squared minus 1, and on top, we're gonna have our u prime. And in this example, u is equal to e to the x. So the e to the x shows up here. Then I gotta square it and subtract 1. And then I put its derivative right here. Its derivative e to the x?
Yes.
Hoorah.
Congratulations.
Credit hours. All right, those e to the x's will cancel. 4x all squared will give me 16x squared. What's the e to the x all squared gonna look like? 2x. When you raise a power to a power, you multiply exponents. So my final derivative looks like 4 divided by 1 plus 16x squared. E to the x's cancel, and I'll have the square root of e to the 2x minus 1 down there. Right? All right. Let's take the derivative of 6x times the arcsine of x squared. So does anybody see a product rule in this? Everybody see a product rule in this? Okay. So we've got a product rule. And then when it comes time to take the derivative of the arcsine, we're using the fact that the arcsine has a square root downstairs of a 1 minus u squared. And then we can squeeze the u prime to the top.
Let's see. Cosine's the one where it's negative.
Right. So we're going to do first times the derivative of the second plus the second times the derivative of the first. So copy down the 6x, and now I can take the derivative of the arc sine of x squared. So I'll start with my denominator with the square root, 1 minus the u squared. So x squared squared. Now I need the derivative of this. Put it on top. So on top, I'll put a 2x. Now the other way, copy down the arc sine of x squared. And multiply by the derivative of the first, and I can just squeeze that 6 right there. Okay? You can put the 2x with the 6x together, make 12x squared over that radical plus 6 times the arc sine of x squared. So multiply these two.
Oh.
Right? We have derivative formulas for e to the x and e to the u. We have a derivative formula for the natural log of u. I want to use a logarithm to help me find derivative formulas for any other number to the x, like 10 to the x or 4 to the x. And I'm going to use a logarithm or some version of that to take the derivative of a log of other bases. So I'm going to derive a couple more formulas.
Is that where they use 10? This is the easiest one.
10?
That's like the log base.
Log base 10, yeah.
Easiest one.
Yes. All right, so let's swap boards here. One to the west. There it is. Okay, so suppose I want to take say 4 to the x. I want to take the derivative of that. There's a couple of ways you can do that.
Well, it's simple. It's just on 4x, or it's, no, it's x4 to the x minus 1.
That gets you the big
Could you do the power
the
thing?
power thing.
Yeah.
What is
could
the
you do
power thing?
You make the base 4.
I can, but I don't want to deal with a logarithm base 4.
You can do
Yes, sir.
natural log.
The derivative of the exponent times in the natural log of the base times
Itself.
Yeah.
Right? E to the x has as its derivative itself. 4 to the x is going to have that as itself. And then somewhere in there, we're going to take the derivative of the exponent and then multiply by the natural log of the base. But here's why. If I take the natural log of both sides, I can pull that power down. Right? I'm going to pull that power down. Once I get it all on one line, I can use implicit differentiation to find y prime. See, now I have a function of y as opposed to the y by itself. Let's start from here and take the derivative of both sides with implicit differentiation.
So x, y,
So what's the derivative of the natural log of y?
y over y, y prime over y.
Y prime over y, right? 1 over y times y prime. The natural log of 4 is a constant, so I've got a constant times x. So the derivative of constant times x is just a constant. So y prime is just y times the natural log of 4. Multiply both sides by this y. But y is 4 to the x. Okay? In general, the derivative with respect to x of any number a raised to the u power is going to have this general pattern. You get itself back, the natural log of the base, then times the derivative of the power. Itself, just like with the derivative of e to the x, it has itself in it. But then you have the natural log of the base. Well, we don't have this in the e formula because what's the natural log of e?
E.
Lower.
I'm sorry,
Natural log of e is 1.
that's what I meant.
And then you have the derivative of the exponent. So for example, if I want to take the derivative with respect to x of 10 raised to the x squared plus 4. So here my a is 10, my u is x squared plus 4. So this derivative should have itself times the natural log of 10 times the derivative of the power. Itself, natural log of the base, derivative of the power. Now for logarithms of other bases, we can use the fact that we have a change of base formula. If I want to take the derivative with respect to x of maybe a log base 10 or log base 2, log base whatever, let's use a log base b. And I'll do it in terms of u. The change of base formula says I can rewrite any logarithm in terms of a common logarithm. I'll use a natural logarithm. This is equivalent to the natural log of u divided by the natural log of b. The natural log of this thing here divided by the natural log of the base. The base is going to be a number. So the natural log of b is also just a constant. So when I take the derivative of this, I just take the derivative of that and then stick that back on. So what's the derivative of the natural log of u? U prime over u. And then I have the 1 over the natural log of b that I just tack on in the end. So if I want the derivative with respect to x of the log base 10 of e to the, I don't want to use an e, how about a sine of x? Okay, so if we want to jump straight down here, or we can put the in-between step in, let me do both. This base is a 10, so downstairs I'll have a natural log of 10. On top I have the natural log of the sine. So here's the natural log of 10, I'll just pull it out front. And now you're taking the derivative of the numerator. 1 over u times u prime, 1 over sine times the cosine.
What happens, I'm sorry?
This is a constant, I factor it out.
Yeah.
Now I'm taking the derivative of the natural log of sine, using the 1 over u times u prime. So 1 over u times u prime. And if you want to put a cotangent instead of cosine over sine, that's fine as well. Yes. Yeah, because the derivative of log of 10 is always going to be 0. So that step that I did where I took the natural log of both sides to bring the power down, that particular technique of using a logarithm to bring a power down is called logarithmic differentiation. And we're going to use it when we have a function whose base is a function of x and whose power is a function of x. So the next thing we're going to look at is how to take the derivative of a function of x raised to a power that's a function of x. We want the derivative of that. For that, we're going to use a logarithm. We're going to use a natural logarithm. Swap back to east. Function of x raised to a function of x. Trying to find an easy one here. Let's start with y is equal to 3x plus 1. And up here, let's just put in x power. Now, the power rule will only apply when the power is a number. I can't bring the x down, raise it to 1 power less, and multiply by the derivative inside. That only applies to real value numbers as the exponent. So instead of doing that, we're going to do what we did with the 4 to the x. We're going to take the natural log of both sides so that we can use that property of logarithms that brings exponents down in front. Once we do that, I have everything written on one line. I can use implicit differentiation. So now from here, I can find y prime. The derivative of the log of y is 1 over y times y prime. On the right-hand side, it's just the product of 2 of our elementary functions. Take the derivative of the product rule. Here's the first times the derivative of the second plus the second times the derivative of the first. And so our last step is to solve for y prime. And I can get this from here to there by multiplying both sides by y. And if I wanted this as a function of x, I can take this y back out and put that back in. Okay. Put this right here. And I'll stop right there. Now we got one more example where I need to show you how to use this. Because logarithms have other properties too, right? The log of a fraction is the log of the top minus the log of the bottom. And the log of the product is the log of the first plus the log of the second. If we have a real complicated looking expression, we can spread it out with logarithms, use implicit differentiation, and we can get easier derivative.
I'm crazy that numbers work like this.
Crazy?
Yeah. Like
Wacky?
They just work.
It just works.
Why do we assume that numbers are supposed to be given names?
What do you mean?
Oh, that's made. Like we had a really good. Why do you need to count over 5? We had a really good tool for that. It was called guessing.
Because one day you're going to hope that you have a big old pile of money in the bank and you want to count it.
Somewhere over 5.
But I'd rather just like trade sticks.
No, you want to sit on your bed and you're going to count $100 bills. You're going to make it rain.
You're good.
Thank you. If you got homework, I got a plane ride today. Great papers on the plane.
Was it 210 of the lost call?
Yes, 201, sorry. The door will be shut, but it's unlocked.
Okay, thank you.
Thank you.
I went
Thank
to
you.
a soccer game and saw you had your own parking spot. It was like.
Which is funny.